Then I'm going to pick another point and take another step of the gradient using the error in that point. And I keep on going. And P is the way I decide to visit the points. It can be a deterministic function where I fix the order. It can be a stochastic function where I do things with or without replacement. Okay? If you pick the points and you put them back in, this is the classical stochastic gradient technique. If you take the point, you reshuffle them and you visit them. And then when you're done, you reshuffle them and you visit them. And this is the reshuffling or technique. Okay? Doesn't really matter. The main point of this is that each of these steps costs less per iteration. And then we have to agree, ideally we would like to do one pass over the data. Oftentimes you're going to do more than one passes over the data. This family of algorithms is often called in machine learning just simply stochastic gradient. More correctly, if you consider also the case where this dependence can be, for example, deterministic, these are techniques that are typically called as incremental optimization techniques. They are typically used when you have to optimize an objective function, which is sum of functions, and you do it by picking each element of this sum term by term, which is exactly what we're doing here. I'm not going to talk about these too much. I just wanted to emphasize a bit the typical behavior that you might observe in a learning scenario. These plots are, again, the empirical risk behavior. This top one is GD. The other white one is the accelerated gradient. So it converges faster and it goes faster to the minimum. Then they get to the same point. The pink one is SGD. In convex problem, which is the one, in particular in least squares, where you can really study what's going on, what you typically observe is that at the beginning, it can often perform very fast. It just goes down very fast. You pick a few points, and it can get big steps in the right direction. But when you get closer to convergence, typically the asymptotic results we have, for vanilla SGD at least, is that it's actually even worse than GD. So it does get to the same point, but worse than GD, okay? Close to convergence. This behavior is documented by the theoretical result. They're somewhat, not asymptotic, but work in a large number of iteration regime. This is an empirical observation, which is not, to the best of my knowledge, quantified by actual mathematical statement. Does this make sense? The question we want to ask is, okay, who cares? If you're doing machine learning, as we did in acceleration, what is the effect of this? Okay, acceleration mattered because we could stop early. What about this guy? Well, the typical behavior, and again, this is more experimental than anything else, is I already told you that this is GD and this is AGD. They get to the same height, but this guy gets there sooner. SGD typically works like this. At the beginning, it works more like an accelerated method. It goes down very fast. Then it slows down. And it actually achieves, you can provably show that it achieved the same quality of GD at the same number of iterations. So it's not faster or slower. And then it's slow. So in some sense, in terms of generalization, it gets more or less to the same point. But then it's slow. It converges slow. So it doesn't overfit as fast as GD. Okay? This can be proved. That the fact that this point and this point coincide can be proved. And this is more of an empirical plot. What does it mean? Well, it means that in some sense, the minimizer of SGD is somewhat flat around this point. So in some sense, it takes big step towards overfitting. Then he gets around the solution. Then his slowness allows him to go slowly towards, so it fits faster, but then it doesn't get close to overfitting that fast because it's a bad algorithm in a way. So being bad here, but good at the beginning, it's kind of a feature of SGD that might turn out to be useful. This is the picture in the regime where we can allow ourselves a budget to see this stuff happening. Again, you can ask yourself what happens if I cover, if you can just see this, okay? If I cover where you can see the stopping, then you can just say, oh, SGD is the best of them all. Because, and I'm not saying that this is always what's happened, for example, in neural networks, but I'm just saying this is indeed something that happens and it's worth investigating, okay? So both the fact that this might be a resilience to overfitting due to the slow properties of convergence, and both to the fact that if you don't get close to convergence, you may actually see SGD as always the winning method. a point when you look at least in neural network literature that you have to be aware of is that this reasoning is typically when I'm looking at least squares, error. If you have actually a classification problem, there could be, it's easier, so you might have some further effect. You know, the picture gets more complicated, but I don't want to comment on that. So this is my last comment about optimization and statistics and the trade-off between time complexity and stability. What I try to convey is the idea that by taking an inverse problem regularization perspective, you can somewhat have a more cohesive study of optimization ideas and statistical ideas, bringing to bear really somewhat features of both worlds, where you discover that optimization itself, in terms of iteration, is a form of regularization. It allows to control at the same time stability, statistical stability, predictivity, and time complexity. So it conceptually is a cute idea, the fact that you can control these two things with one single knob. The big issue that we haven't discussed, and then if you want this idea of, okay, why accelerating is interesting or not, why SGD could be interesting or not. The thing that I haven't discussed, and that's what I want to do next, is discuss a bit what you do if you can push this idea. I like to call this, when I observe this kind of stuff, I start to call it in my head computational regularization. The idea is you can use computation to do regularization. And then again, then you start to be interested of how many tricks, computational tricks can you use to some extent. And one big challenge up to now is that we've only been shaving off time complexity, but we've not shaved off any memory. So the memory is always, the nonparametric memory is always n squared. Now, depending on how you want to do it, if you do gradient methods, you might compute things step by step along the line, but say, roughly speaking, we haven't really worked to improve memory much. And so that's what we want to discuss next. The reason is that everything I discussed is bounded in memory to n squared, roughly speaking, or a lot of pre-computation all the time. And this means that we cannot use this on data sets that are common these days. We can get these up to, say, 40,000, 50,000 points, and then you have to start to do approximation, and everything I says just falls apart. So what we want to do now is discuss if we can, at the end of the day, I would like to show you that you can actually pay the price of randomization, making your algorithm randomized. You can actually introduce a family of algorithms where one knob is going to control at the same time the stability, the time, and the memory complexity of your method. So that if the problem is hard, you need to use more memory. But if the problem is easy, you need less memory. And so in some sense, you close the loop. And I hope I get time to get to the end. We're basically showing how using this idea in conjunction, again, with optimization, you can actually get a pretty fast algorithm that work on large scales. All right, so So what we want to discuss is an idea, again, that is classical in inverse problems and somewhat tweak it, and is idea to using projection in conjunction with regularization. So the idea is I'm going to consider a sequence of spaces all contained in my space H. And I'll consider for each of them the projection of H into this space, okay? For now, they're just abstract, okay? Then we're going to make example in a minute. Suppose that you have them. Then the idea is that what you're going to do is basically that you remember that empirically I have this problem. This is my starting point empirically. And what I'm going to try to do is basically to, or if you want this problem, instead of doing this, I'm going to replace this f by a projected version. So instead of this, I'm going to insert here my pi. So I get Sn, pi, f, let me call it pm, minus, okay? So instead of working with function, I first project them down in m dimensions. M is going to be the dimension of the space. And then I just work on this reduced set. I don't have any constraint. But if you want, this is not a sort of constraint set. So in some sense, this is a more of explicit. I don't write it as a constraint, but I could. I'm really restricting myself to a smaller subspace. Okay? So this idea is very, 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 very well known. What is the canonical example of projection that is used in inverse problem? Anybody is in inverse problem and use projection method sometimes? The most common way to build subspaces is just saying, well, let's just look at the eigendecomposition, the singular decomposition of this operator, and just look at the spectral projection. Okay, so you say, just to introduce less object, you look at this guy, introduce his eigenvalue and eigenfunctions, and then you take this projection on the first m eigenvalues. Okay? Now, depends who you are. You can call it a truncated singular value decomposition. You can call it what is called in statistics principal component regression. So you do PCA, and then you do least squares on the dimensionality reduction, the data after dimensionality reduction. So you just do PCA and least squares, and you don't do anything else. You don't add anything else. So this is what is called principal component regression. If you want, this is the kernel version of principal component regression. In this case, you can really solve this problem exactly. I'm gonna skip this, but the basic idea is that this is the only, if you use PM to be the spectral projection induced by the operator, this is the only one case where you don't need to do anything else. Why this should be the case? In all the other cases, if you take other projections, which are not the one induced by TSVD, you will have to add, for example, a penalty like this. And you will have to play at the same time with projection and regularization. TSVD is the only projection that doesn't need lambda. Why this should be the case? An intuition? In some sense, the idea is that our algorithm are the old algorithm we study, throw away the small eigenvalues. Okay? So if you use a projection, you have to be sure that it's somewhat aligned with the eigenvalues, the eigenvector. You know that you want to project all the algorithm we've seen so far in a more or less brutal way. They project on some principal eigenspaces. So Tikhonov doesn't quite project in the sense that it doesn't kill the small eigenvalues completely, it just depress them. So it's not strictly speaking a projection, but morally that's what it does. Okay? And you can make this precise. He just consider essentially a subspace spanned by the first few eigenvectors or eigenfunctions. Okay? Landweber iteration, through its iteration, does the same thing. If you project, in some sense, if you're aligned, it's a good idea. Otherwise, you have to be sure that you have a projection which is somewhat aligned in a good way. And it's hard to do it a priori. If you know the eigendecomposition, you can build a projection. There is somewhat a rotation. So I think of this as a basis. There is the right basis, order in the right way. You're not going to take another one. And you can ensure that it's not too misaligned. But you have to compute this first. If you want to do this uniformly over all possible operator and eigendecomposition, you cannot ensure this a priori. And you see from theory that really some terms can blow up. And so if you take a projection other than TSVD, you need to use this in conjunction to regularization. Does this make vague sense? This is by no means something new. The idea of using projection inverse problem typically arises when you have a continuous problem, an integral equation or a PDE. You discretize it, and you derive a finite dimensional problem. And then you have to be sure that whatever you've done is stable, that you didn't start to move around the small eigenvalues too much. And so the name of this kind of stuff is typically regularization with projection. Again, when you use, say, least squares methods, quadrature methods, Galerkin method to discretize, typically you do regularization afterwards because you don't have the control to ensure that your discretization is really going to capture only the principal subspaces. Okay? So there is a large literature on this. Least squares, dual least squares, quadrature methods, Galerkin, this is all in this. This won't be enough for us to try to do something useful. We're going to consider a special case, which is a case where we allow ourselves to use not just projection, but stochastic projections. Okay? And this is going to just revisiting an idea which typically go under the name of Nystrom methods in the context of machine learning, which is kind of an abuse of a name of a technique that is known to discretize integral operators. And here is somewhat used as a general name in a slightly different meaning. So the idea is the following. You see the theorem over there where I have that my f of n is a linear combination of kernel at the training set points. It means that I'm considering function that belongs to Hn, which is a subspace given by kx1, kxn, where x1, xn are the training set points. In all this theorem, I don't need to consider larger subspace than that. So this is going to be the largest subspace I want to use. But what we're going to do is that we're actually going to build spaces Hm, which are, sorry, this is this, what I meant here is the span, the linear combination. What we want to do is that we actually consider a span of m points. Here m is always smaller than n, and x1, xm is some subset of my points. Okay? So I'm not going to use all the points to parameterize my functions, but only a subset of them. The key point, and this is really important, is that I'm not throwing away my data. Okay? I select a subset of the input points to write my functions. And then I still use all my data to compute a solution. So my algorithm is going to look like this. If you want, I'm going to consider the projection associated to this method. Okay, so PM is the projection on this space. And this is, I just rewrote what I wrote there, okay? So you see, I still use all the data. It's just that my function are not generic function in H or combination of all the possible points, but I restrict myself to a subset. How do you choose the subset? There are tons of ways. The one way we discussed the most, and I'm going to give you results for, is uniformly at random from x1, xn. So you pick m indices from 1 to n, and then you go in, and among this point, you pick this m. Okay? That's what we're going to do. And then we're going to discuss, I'm going to comment a bit of whether this can be improved and how and what do we know and not. Okay? But this arguably is the simplest thing you can do. So far, so good? So what we want to know now is understand a bit more what we're doing. And we can start by, I'm going to give you a couple of equivalent formulation of this problem. And we're not going to prove them, but hopefully they are reasonable enough. So what did I do here? Instead of writing, oh, sorry, maybe here I should put an F. And there's still an F. Instead of writing the F, instead of working in the full space and projecting, I absorb the projection in the F. So here I work only on the subspace. Okay? It's easy to see that these two problems are equivalent. It's a change of variable, essentially. Then notice one thing. What does it mean to be in the span of this point? It means that we are looking at the function in H that can be written as f of x, no, let's say f equal sum kxi tilde ci 1 to m, where c1, cm are numbers in R. Okay, that's what it means. Correct? Just a linear combination of these m points. If you define this to be exactly an operator, let me call it zeta m star, okay, applied to a vector C. It's basically is similar to S star n, okay? Let's call it S star. There is just a normalization difference, okay? So let me call it S tilde m, okay? S n, take a function and evaluate at the point. S star, take a vector and turn it into a function by combining the kernel according to the weights. This guy is the same thing, but he uses not all the training set points, only the one I sampled, and not n of them, but m. Okay? The only difference is that if you remove, there is one normalization factor, 1 over n or 1 over m. I'm throwing it away for now. Is that okay? I'm doing this because now we can plug this expression in here, and then we derive a matrix formulation. So again, I build my subspace with its projection. I get back to exactly the formulation. I rewrite it as just a minimization of function in this space. And now I show that, you see what I did here? I'm basically showing you that this space is actually parameterized by a vector C, which is in Rm. So I want to rewrite this now just as a minimization over this vector C. And again, the idea is to show that there is another problem which is equivalent. And this problem is just the minimum on C that belongs to Rm of, I just have to plug in that expression, I write the norm explicitly, so this is going to be S tilde star MC S tilde star C. Okay? So I took F and I replaced it by zeta star C, and now I optimize over C rather than zeta star, and rather than F. Okay? These three problems can be shown to be equivalent, and the thing that now I have a finite dimensional problem. If you want, before, at the beginning, when we introduced Tikhonov, we said, oh, if I work in an infinite dimensional space, I have still to prove that I can always parameterize by a finite number of parameters. Here, I'm basically starting from the idea that I have a finite number of parameters actually smaller than n, and here I'm just rediscovering this from a numerical point of view. Why do you care about this? Because essentially, these are now just matrices. This is a matrix, let me call it KNM. It has n rows, m columns, and the entry ij is just kxi, k tilde xj. Okay? You can check because of the form of these two that I'm just taking product of the training set points and the one that I selected, and I just get the matrix. And here, rewrite this as CS tilde M. This matrix here is what I might call Km, and is the matrix whose entry ij are k, x tilde I, x tilde j. Usually, yes. Thanks. Okay, now let's stop. Now this stuff is going to become very concrete. Okay, it's going to be very obvious what it is. The standard kernel ridge regression estimator was based on computing this, solving this linear system, where you have this big kernel matrix, big vector, and a big vector. Okay? What do you do when you do that? If you just take the derivative of this, you just get the following expression. KNM transpose, KNM plus lambda K M, that's it. C K N M transpose yn. Okay? Just the derivative is set equal to 0, and you see what you get. You get this expression. So this matrix is of size n, and is this big matrix. Let's see what we have done from a pure linear algebra point of view. Forget about eigenspaces and stuff. What did we do? We took this big matrix, and essentially we sample uniformly at random a bunch of columns. And we work on this reduced set. Because we don't want to freak out, I'm just going to assume that at some point I put the column at the beginning, which basically means that I'm just, instead of the full matrix Kn, I'm now working with this matrix, which is Knm, where you see that I'm not throwing away the data. I still have n rows, but only m columns. And the thing that now, I don't have to work with the full vector, but only with this smaller vector. Okay, so from a linear algebra perspective, I give you a huge, ginormous linear system, symmetric positive definite matrix, and now I'm just going to pick a bunch of columns and define a reduced system, and then just solve that reduced system. Okay? What do we gain? Well, our algorithm has become randomized. But you see that now, how much does it cost me to do this? Well, this matrix is m cubed. Building this matrix cost me m squared. And storing this matrix is going to cost me nm. So if I pick m equal to n, I've done nothing. I have the perfect statistical results as before, and I gain nothing from a computational point of view. If I pick m smaller, hopefully much smaller than n, I clearly have a potentially ginormous gain, both in time and space complexity. And the question becomes, does this come at the price of a statistical accuracy? And the answer is no. There is a whole regime where you can subsample this matrix and get essentially the same statistical result in expectation or with high probability. It's a randomized algorithm, so this is going to be both on the data and the way you sample. Why would it be the case that I can throw away a large chunk of a linear system and still essentially find a solution which has the same statistical quality, you think? It cannot be true in general, right? If you give me a generic linear system and I throw away a chunk of it, there's no hope. So we must have somewhere made assumptions that make this possible.
The data originally was low-dimensional?
Maybe, but we didn't say it, right? So he's saying maybe the data were low-dimensional. Maybe, but we didn't make this assumption yet. Any idea? Not that I see that I'm not sure that, definitely it is, but I'm not sure that, well, I guess, well, you have to elaborate more to, unless everybody's convinced.
You have kept all the data.
Sorry?
You have kept all the data.
I kept all the data, so a good point is, well, a good sanity check is, unless there is some special structure, if I throw away data, there's no hope that I can, of course I'm going to lose some statistical accuracy. So the fact that I still keep as many rows as the data, at least gives me hope that it's possible, but it doesn't quite convince me that by throwing away a substantial amount of a matrix, I can get the same solution. I mean, if I give you a linear system and you just you know, divide the matrix in half and you keep only half, you don't get the same solution. There's something else going on. Well, the key point is that throughout these all lectures, we work with algorithms that are going to throw away small eigenvalues, right? And in the case of PCA, this is done explicitly. What you do is that you take the matrix, the full matrix, you compute its eigenvectors, you store the whole thing, you compute the whole thing, and then you throw away a bunch of them. Okay? And that's the way you proceed. It's really the way you proceed. So the question here is there an implicit way of doing it? And instead of pre-computing everything, and then throwing away, you just compute less. And the analogy, to me, is a little bit in philosophy with what people do in compressed sensing, where you say, instead of acquiring and then compressing, acquire less. Here it's not quite the same, but has a similar flavor. And you use the same kind of randomized sampling idea to somewhat get your measurements. In the case, the measurements are these columns. This idea is by no means new. It's basically been one of the big trends in linear algebra, where this set of ideas are broadly known as randomized linear algebra. Okay? And also if you're just reinterpreting this from a learning and a projection regularization perspective. The novelty is that typically in linear algebra, you have a linear system, you just want to solve it fast, and that's it. Here, we want to actually view this as a device to get good regularization. So there's something below, right? Yeah. Remember that for Tikhonov regularization, we had the result that says that if you pick lambda n to the minus 1/4, then with high probability you get something like this. What happened if you, sorry, I didn't give a name to that guy. I want to call lambda n m, the solution that I obtain after my projection on the first m columns, right? So you have to choose lambda and the number of columns now. Does that make sense? F lambda m is the solution of that reduced linear system. And the result here says that essentially if m, sorry, this is 1/4, and this says that if you pick mn order 1 over lambda, you're good to go. You get exactly the same result. Okay? This result is not, I simplified a little bit, but it's not self-contained proof that we can do in short time. It's a bit longer. There are a bunch of, there are not just 2-3 terms, there are more, and you have to some little more advanced tools to do it. It's nice because it shows that really there is an entire regime. So this is a big, there is much less than n, right? It's just n to the 1/4. And you see that now we get much better complexity. Essentially, the complexity needed to get optimal statistical rates are so this is the time complexity, and this is the space complexity. Okay? So again, if you do that many computation, you can solve the whole thing without losing statistical accuracy with high probability. Now, this starts to be more substantial. There are several remarks. First of all, again, we're working in the optimal bound regime. So we know that we lose nothing. And we show that indeed we can subsample without losing any accuracy. We can play the same trick that we played before where we have Tikhonov regularization. You can swap the role of these two guys. Instead of parametrizing m in terms of lambda, you can actually parameterize lambda in terms of m. The good news is that that algorithm over there is just a matrix inversion. So it's really, what you can do is that you can actually give a very fast way to update your solutions. And you can proceed like this. You just pick one solution at random, one column at random, say maybe say 5 columns at random, and solve this linear system. Then you find the solution, and now you add one column. You don't need to recompute everything from scratch. You just have to update your solution. So exploring the different M is actually pretty fast, okay? And now you can do a plot where what you're doing is basically putting M here, and you can now look at your test error, cross-validation error, and you're going to observe exactly something like this. M is lambda, lambda is M, is the same thing, and this guy is controlling the stability or statistical properties of your method. The only thing is that now, this one point here, okay, depends on the quality of your problem again, how hard or easy it is. And so by this, because M controls at the same time both the time and space complexity, this does exactly what we wanted. It provides a method where there is one parameter which at the same time controls space, time, and statistical stability of your solution. I wanted to say something, but I forgot. So this, if you want, was one of our goal of the day, to try to see to which extent we could use this computational idea. Yeah, the thing I wanted to say is that compare this to, again, when we did optimization, we typically say, when you're doing optimization, you just say, I'm going to pick a number of iterations as large as possible to be close to convergence. Once you realize that optimization is doing regularization, you say, no, 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 no. Let me cross-validate that and just get the right amount. If it's a lot, I'm going to use it. Otherwise, I'm going to stop before. Here, the same thing happens. If you look at, this idea is not new. The algorithm I show you is not new, okay? People do this all the time. But the way they do it is just basically change. Let me check my disk and see how big it is. Then I'm going to pick M, the largest possible memory, largest possible number of columns that allow me to store this matrix, and then I use it. Here, instead, you say, no, 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 no. Start to explore M, and stop when you don't need any more columns. If you need them, go up to the memory budget. Otherwise, keep on going. It's exactly the same kind of philosophy. And as I told you, is this kind of philosophy where you think of computation as regularization, and you just look at the trick and say, oh, people do this to save memory. Is it stabilizing the problem? There are a bunch of directions in which you can go. For example, one of these directions is the one that to say, can you do something better than uniform sampling? Uniform sampling allows you to get the job done and gives you this kind of behavior. Can you do something better than that? And yes, you can do. Under more assumption, in this kind of scenario, no, it's actually is doing already the best. But you see, this is the best, but we don't know if this is the best. We know that the statistical bound is optimal, but I cannot tell you that this amount of memory is optimal. A very nice theoretical question that goes in the realm of complexity theory is the one that says, what is the minimal, if I fix the optimal rates, what is the minimal computational cost required to solve the problem with optimal rates? This requires a complexity theory argument where you define what does it mean to have an algorithm and so on and so forth. So we don't know that, but we know that we can further improve that in some scenarios. In particular, in the cases where you have some eigenvalue assumption on the operator that defines the problem, then techniques that use more complex sampling can work. The kind of techniques that are used is what is called leverage scores. I just want to mention it, but I don't want to discuss it. It's basically based on, it's a method that basically in principle requires you to solve the original problem exactly. Okay? It's basically you take that matrix there, you invert it for real, and then you take the element of the diagonal. And then you use these scores to sample. If you could do that, then you can get that a much smaller number of features might be sufficient. Of course, at this point you say, well, if I can do that, why don't I just solve the problem and don't do anything else? The thing is that the result is robust to approximation on the way you compute the trace. You only need the trace of the inverse, and you can try to approximate this in a fast way. And people have done this. I don't want to show it to you because we've been playing with this for the last 2-3 months, and we see no improvement whatsoever on some 10 data sets that we've tried so far. So it's actually very nice theoretical ideas. The results are much different, and I invite everybody to take a look. But I want to spend time on it because so far I haven't seen a big advantage from a practical point of view. Theory definitely suggests that the advantage is really, really big. All right, so this is almost the end. In this last segment, I wanted to show you how, if you allow yourself to pick an idea from inverse problem, combining regularization and projection, but you further combine it with the idea of making the projection stochastic, you can break the n-square barrier in terms of memory and really going down toward having linear algorithms. The results I show you, again, are worst case. You can put now different alphas, and you can further show that there are situations where you can make this really become as close as possible to linear. The whole point of this is just showing you how, again, relatively simple ideas can be actually understood in the same framework of everything we discussed. You can put a lot of ideas in randomized linear algebra, perhaps not so surprisingly, in the context of regularization for inverse problem, and in particular the inverse problems of learning, where what you have to do is just to consider not only in some sense you have to consider also the stability properties of the method. The take-home message here is that up to now, we somewhat discovered that different principles that you often use can actually be seen as regularization. So optimization, and if you want this, you can think of some form of dimensionality reduction. Dimensionality reduction per se, stochastic projection per se, do inform a way to stabilize. And the whole game here is that you don't get something better statistically. You just get the same statistically with less memory in less time. Questions about this stuff? Yeah.
Let's consider the support vector machine case. Not every data point is support vector. So in this case, maybe we can use less memory and take some data and drop the data that is not very important.
So the question is, if I understand, in supervector machines, you change the loss. You don't use the square loss. You use the hinge loss. And you get that the solution is sparse. You get a similar effect that rather than using all the points, you only need a subset of the points. And the idea is that this geometric interpretation that you're solving classification. So if you're not close to the boundary, you don't need them. Theoretical results actually show that at best, the number of supervectors that you need is anyway a constant factor away from the total number of points. Okay? This shows that you can actually go down a square root or more. Here is n to the 1/4. So you don't have just a constant factor less points. You actually have order of magnitudes less. Okay? If n is 1,000,000, that's much less than a constant of 1,000,000. So in some sense, there is a different regime. Supervector gives you similar results in principle, but quantitatively is much different. This result is much stronger because it's a much bigger reduction. Other questions or survivors? Yes. I'm going to repeat the question, John.
Thank you very much. In the TSVD method, so far I understood that you have to pick the K, for example, principal components. Have you ever heard of any way of selecting the components that you will use?
No.
No? Because, for example, you don't need the first component as to make a prediction on your data?
No.
No? Ever?
I swear, no.
Okay. Thank you very much.
I haven't looked for it, though. I mean, here I really just want the first few always in this game, so I never did. No, I know that. I know a bunch of reasons why, but I never. So okay. Don't take my answer as anything useful. I didn't look for it, so it's a very weak statistic, the fact that I don't know about it. So, was a question? No. So let me make one comment, and when we go towards the finale here. If you don't come from machine learning, one thing you can ask and say, if you've been doing signal processing or inverse problem, you can ask, world has moved on from L2 regularization in the last few years. Why have you been talking about L2 regularization for 3 hours? Okay, and we're actually 3 hours doesn't quite, it's like more 8, and it's very warm. So the reason why is because the problem we're looking at are typically places with the function space, the function are defined on complicated spaces. Our X might not be images, might not be 1, 2, 3 dimensional, might be graphs, might be strings. Building kernels is complicated, but building a basis that you know are going to make your function sparse, it's much worse. So while we know wavelet, shearlets, and whatever lets you've been using in your life, give me an example that really makes things sparse in dimension bigger than 10, or maybe even better in dimension 20,000, where 20,000 are crazy numbers taken out by somebody in some measurements. So while the idea makes sense, and in think mathematically and theoretically you can do it, it has not paid off as much as is done in other fields like imaging, for example. And not because it's not a good idea, but because it really reflects the fact that we don't know how to build bases to make our function meaningful, sparse in a meaningful way. And so oftentimes, even maybe there is a set which is sparse and it's good, just using an L2 norm where you have completely rotation invariant gets you as far as another more complicated method where you don't know how to pick a good basis for your sparsity. And if you look at, say, your total variation, other techniques, also in this case, they're not as easy to pick. When you really want to do sparsity, and it's typically where your goal is not that much prediction, but is really to understand a bit more, say in the case of variable selection, then you typically take a linear model where your goal is really to just select the variables, and then it's worth doing that. So the biggest impact, in my view, has been in these kind of cases. Okay? Of course, this is a bit of a biased view, and there are many cases where perhaps instead of vectors, you're looking at matrices. For example, matrix completion, that's not true. You can get pretty good results using trace norm regularization. But in some sense, if you look at the classical prediction problem, how to learn a function that's going to do well on new points, which is what we've been discussing so far, well, I really would like to see real data where you really see that an L1 or a more generic different than L2 regularization approach really gives you a ginormous boost. Okay? There are some cases, but on average it's less dramatic. So this is partially the reason why this stuff is still useful on top of your pre-processing. Perhaps I'm just going to use slides here, and I just want to show you one more thing and call it a day. I know. It did it sound. Or maybe it's happening. Or maybe you do it. Now that we recorded this, he can do it. Oh, it's okay. We fall asleep. Oh, that's fine. Let's see. It doesn't appear anyway, so. Yeah. Stay away. Yeah, so as you see, shall I do the... No. Okay, so I could write this on the board, but I think you're tired and I'm tired too, and there's not going to be a lot of stuff a lot of elaboration to do. So I think slides will be enough. And I picked the slides because I want to show you some of the results. I'll give you somewhat of a feeling of what we're doing and how far we are in this kind of reasonings. Of course, at this point, you can say, OK, you did optimization first, and you did randomized linear algebra. Why don't you do the whole thing together? And I'm going to do that, and I'm actually going to do a little bit more. We use the last trick that we haven't used so far, which people love, which is preconditioning. OK? Let's remember a second what is preconditioning, why it's useful, and then show you how we can use it. No. Yes. No. No. So the basic idea of preconditioning is, you have a linear system? Well, actually, try to define another linear system equivalent to the first with a better condition number. Why? Because if you can control the condition number, you can make the number of iterations needed by an iterative solver much smaller. I'm going to illustrate this in our context. The notation is slightly different. Rather than the n, there is a hat, but it's the same stuff. This is the empirical ridge regression problem, and this is the big one, okay? It's the one with every row and everything. The one on the left is the exact problem of Tikhonov regularization. And on the right, there is the idea of passing to an equivalent problem. You have to introduce a metric B, okay? And then you're going to pre-multiply by B transpose and afterwards by B, the linear system, and your data by B transpose. You get a new parametrization by a vector beta. And then given this beta, you can go back, okay? The question here is, why would you want to do it and how you would do it? The reason why you would like to do it is because you can make the number of iterations much smaller. For example, again, similar to the comment I made before with better sampling, if the ideal thing to do is to pick this B so that BB transpose is actually equal to the inverse. Of course, this is not very practical, but let's see what this would do for us. You remember that in our theorem, we had this kind of T over O 1 over lambda kind of behavior if you optimize. Well, if you actually look at this problem, you will actually need a constant number of iterations to get to the optimal solution. So this would be ideal. Clearly, the problem is that you cannot compute this. So people have been doing this recently in a bunch of papers. They've been considering this linear system and try to find good way to approximate this linear system, and they try to find good way to approximate this preconditioner, okay? Suppose that you manage, what do you expect? You're going to lose something here, but hopefully you get something much faster than this. The problem is that we took a step further in the idea of making time complexity better, but with respect to what we just discussed, we took a step backwards with respect to memory, because we're dealing with this guy. And this guy is big. So now the question is, can we put everything back together? No, because this doesn't work. So this is the basic idea. Instead of starting from the ridge regression problem, use random projection for the first time to consider a reduced problem exactly in the way I told you. Okay? That's real. Let's check. So you use random projection once, and instead of the true system, you now consider our reduced system. The notation, again, is essentially the same one I used here. Then the idea is that you want to do preconditioning. The ideal preconditioning is what? Is the inverse of this matrix. But if you do that, you don't gain anything, okay? Because you already solved the problem. So the idea is that rather than using this matrix here, which again, it would be this matrix transpose itself, okay? What I'm going to do is that I'm going to just take this upper corner and take it square. The idea is that this is a reasonable approximation. And if you want, I'm using random projection twice. Once here to reduce the system, and once here to further reduce the preconditioning. Then what you do is that you just proceed in the standard way. And if, for example, here I just show you the basic gradient descent iteration on the reduced system with the approximated preconditioner. So to the best of my knowledge, even in standard randomized linear algebra, the idea of doing the random projection step twice has never been investigated. So the idea of doing preconditioning, a lot. The idea of using random projection, a lot. The idea of using some kind of approximation, yes. But the idea of using random projection twice, Never. And partially is because you see that now we know how to generalize this a lot, but we somewhat use the structure of our system. We basically decided to use this KMM because it seems like a good idea, square, because it seems like a good idea to approximate this product. Okay, so this is the algorithm we call Falcon, and for absolutely no reason. And this is not actually the real algorithm. It's the baby version. Why? Because we don't really want to take this inverse, and we don't really want to use the gradient descent because it's slow. So the actual algorithm, so it's my computer that sucks, is that we replace gradient descent with conjugate gradient, and for what matters, you could have used any other acceleration. And then rather than computing the inverse directly, we use a Cholesky decomposition to compute the various pieces, because this makes it faster and more stable numerically. And this is the actual algorithm, and this is the logo of Moto Guzzi, because it's a nice falcon. Okay, now you can ask yourself, what can you prove? And it's going to look very similar to the theorem I showed you before. 1 over square root of n, choosing lambda over like 1 over square root of n, as usual. We're going to choose m as square root of n, but now we can choose t, the number of iterations, as log n. Okay? So we really kill basically the number of iterations now. The preconditioning does the job. We go back to Tikhonov because by following lambda, we can precondition well. And then we get exactly the same optimal rate. So if you see here, there was an nm square. Here we just shave it down, and we go to nm tn, where tn is just a log n. All right? Now you can produce a ginormous, incomprehensible table if you want. Where basically the attempt of this is basically showing you that at this point, if the rule of the game is let me show algorithm and let's check what is the best known complexity to achieve optimal rates, this is what we know up to now. Okay? One point to notice is that because we use random projection, our algorithm is actually when you have to use the function, it only depends on square root of n parameters. So the actual evaluation, the testing, is pretty fast. If you have 1,000,000 points, you're just going to need 1,000 points to make your prediction. This is important because, for example, say a competitor to this kind of methods is a simple aggregation method where what you do is that you have your data set, you split it in m groups, and then what you do is that you solve the problem in each group separately, and then you recombine. This is what is called divide and conquer. What you see is that this method, in fact, not only it has a worse complexity, both in terms of time and space complexity, but at test time, it requires a complexity which is order n rather than square root of n. And here is similar. The stuff that is in here is the exact solver, the SGD, block coordinate descent, and then all the other methods I showed you before this. So combination of Nystrom and iteration, more or less accelerated. So in my life, typically when I get to this point, I show a bunch of experiences where basically we checked that we didn't make any obvious, we were not naive anywhere, and we just got some decent result. The result we got in this case are a bit nicer, and I want to show it to you. This is the typical picture you see when you compare our precondition method to accelerated method with projection, but without preconditioning. So this is us, and this is a couple of different accelerated projected methods, but without preconditioning. So the number of iterations is oftentimes in the order of tens, even on big data sets. And this is just a qualitative thing. These are more of a quantitative result. We pick 5 data sets, and the rule of the game is pick data sets where you have more than 1,000,000 points. And our complexity depends primarily on the size of the points, right? Because we just end up with the number of a matrix, which is the size of the number of points. They have different size. None of them is very big, or the ones that are big are sparse. Okay, so the size of the input data is not so big. But again, our main priority here was comparing nonparametric methods that work with the full data set. And what you can see here is that basically In all these data sets, these are pretty generic. Some music data, some speech, and some text. The thing is that if you look in terms of accuracy, the method does typically better, but not incredibly better. Okay? I wouldn't sell this as you just blow everybody away. Here is the best. Here is the best by a bit. Here is not the best. There are some results that requires a fairly complicated framework developed, I believe, at IBM. The key point is actually more this column. Because you see, whenever you see a symbol is an algorithm that has been run on a cluster or a set of GPUs or on the cloud. Our algorithm runs on a workstation with one GPU. And in most cases, the difference is either incredible or huge anyway. So here is 55 seconds with respect to the best, which is 289 hours on a cluster of E8 EC2. In this case, it's 20 minutes, and the best is 42 on whatever is the other thing, cluster of 128. Okay, so all these are pretty impressive, and this it's nice because to me because it goes somewhat in the direction where even if you have 10 million points, if you want to understand what's going on, rather than have to wait a week cycle before you can try a different idea, here you can, as long as you can restrict yourself to, say, millions of points and not tens or hundreds of millions, you can have a cycle of results in order of a day, okay, when you can try 3 things every day, and maybe for a week you run on an even larger corpora. We ended up, so one funny thing is that in a world where everybody hail at endless amount of data available, for poor mortals that are not friends with people in Google, Facebook, or whatever company, there are actually not that many data sets with more than 1 million points. And it turns out that the only people that are drowning in data and willing to share with everybody are physicists at CERN. They produce petabytes of data every second, and they throw away 1 million times more. I don't know. I forget the numbers because they don't make sense when they tell you. It's like order of magnitude that don't make sense. And they share data sets like this, which is a couple of millions, this, which is, I believe, 11 millions. The dimensionality is typically under 30s or 20s, so that's not the point. But you still have to deal with these 2 million by 2 millions or 10 millions by 10 millions matrices. They love boosted decision trees. Until a while ago, that's what they used all the time. And then a few years ago, it came out a paper that actually used compared neural networks and then deep neural networks, which basically means neural network meant just neural network with one layer, and deep neural network means neural network with more than one layer. Nothing fancy, okay? No convolution that, drop out this. It was just a vanilla neural network. Still, it gives a pretty big improvement. And what you see here is that on this one data set, again, in 4 minutes, we get this number. And this is what you get with the deep neural network within this time. Okay? And here, the number of parameters of our method is 5 times smaller than the number of parameters here. This data set is the bigger one. And here, the story is the match, I hope, is not finished yet. Here you see, in 3 hours, we get this number. We take 1% off the benchmark, previous benchmark, but we're still some kind of roughly 6% of the deep networks. This runs, and I think we probably here hit our bottleneck. We have 100,000 parameters. They have 500,000 parameters. We cannot run it on our single machine. You know, we have 3 hours, but we run out of space to invert our matrix. Our method is limited in the fact that at some point you have to do Cholesky decomposition of a matrix, which is m by m. And at this point on our memory, we can go up to 100,000, 120,000 max. Okay, so we ran out of juice, and now we have to really do whatever these guys are also doing, which is using more than one machine. So we probably hit our cap in terms of what we can do in one machine. The thing I would like to emphasize is that in this game we've been playing, the nice thing is that by bringing really optimization and numerical linear algebra, inverse problem to bear, in the end you can get something. You just have to borrow things. And this really help a bit avoiding just an empirical trial and error in just speeding up stuff. The big challenge here is following this line of reasoning from more numerical point of view is basically jumping ahead, and probably we can squeeze a bit more from a single machine, maybe get a slightly better preconditioning, maybe variable metric, maybe some kind of aggregated stochastic methods, but then we really have to push it towards multiple machines. These are the two obvious directions. There is a dream to try to use more structure. Right now, we treat every matrix as just a positive definite symmetric matrix. There should be more structure in the data that allow to somewhat explore the computation in a more principled way. Right now, we just select columns. The thing is that all the techniques I know in this context, say multiple methods and hierarchical matrices and so on, are typically limited in the class of the dimensionality of the domain of functions they use. They, dimension 2, 3, 4, 5, 6. We try to use them, but if you go in higher dimension, we haven't managed yet. So we're trying to understand how to go to really hundreds of dimensions. I'm mentioning these as, things where we don't know the answer yet, not when I'm just reporting a point in the curve. The biggest thing here from a machine learning perspective is to somewhat going in the direction I mentioned now, and more in the direction of opening the black box kernel. Right now, the kernel is just a black box. But as I told you, typically, people these days spend a lot of time trying to actually engineer very nice architecture, and that's somewhat what deep networks seem to be doing really well. They can build in a recursive way complicated kernels, if you want, but not just by design, by learning. The hope here is to try to some extent to isolate the designing size of the story, where you have to, say, do a convolutional neural network with convolution of a certain size, subsampling of a certain size, renormalization of a certain kind, and then the last part, where you just do the fully connected part. I view this just as the fully connected part of the story, not as the feature extraction side of the story. The idea is not to maybe be able to beat all this, but to see how far you can go catching up. Up to now, we don't know how well any algorithm on top of a feature extractor does, because we were not really able to train things like a supervector machines on 10 million points. We don't know if it doesn't work, because we cannot do it. So this actually provides a tool to do it in an amount of time that has large margin of progression, and we can check how far you can go. And there are many situations where once you get some good features, you can just reuse them. Okay? Even in images and computer vision and problem where deep networks are important, once you pre-train somewhere else, you can often just use them. And there are several cases where something like this perhaps is useful. The last thing I wanted to show you is really more like a small little experiment. So what we did is that we can now train on, do you know what ImageNet is? Is this object recognition data set, which is 1 million points. I think it's 1,000 dimension. And up to yesterday, we didn't know how to train on it, because we just get too slow and too small machine. Or we have to really work on clusters, and we don't have them. So what we did right now is that we just cheated, if you want. We only wanted to see if we could, so these networks, we wanted to compare with deep networks. Deep networks where we have a bunch of convolutional layers. These are layers with some special structure. And then on top, they have a bunch of fully connected layers, which are just vanilla neural networks with the one from the 1982, say. So what we did is that we took the trained network, and we chopped off the top part. And rather than using the neural network, we used our algorithm. And now we can train on the full ImageNet data sets in a few hours. Okay? On a single machine, I think it takes us roughly 5 hours, if I remember correctly. And these are some numbers. And this shows that, roughly speaking, you get the same result. Okay? This is not satisfactory completely because we are still using the features that are tried by the deep network. It just shows you that, to some extent, the fully connected part, once you have done that, can be replaced with something that can do faster with prediction time, which is roughly of the order of square root of the number of points. Again, in our case, again here, our bottleneck is that we could go up to 100,000 parameters. And if you look at some of the network that works here, they have millions of parameters. So there is a bit still of a question of to see how much stuff you can squeeze on top of these features once you use more than one machine. And I can actually really just, these are really more or less the contribution of this whole story. But that's the end of, you can ask me anything because this is the end of it. Sorry, I interrupted you.
Yeah. No, I just wanted to say that in this case, because you use the already learned feature, actually the number of parameters in your case is the same as what they do. It's just because if they could do the same as you do. Right. Okay.
Yeah, what I'm saying is that if I want to try to go a bit deeper, I have to, if I don't want to use these features, I have to use more parameters. That's what I was trying to say.
So for Falcon, or in general, did you manage to kill the lambda? Just only aim to do regularization?
In the case of Falcon, no. In the case of Falcon, we go back to just using lambda as a regression parameter because the number of iterations is typically so small that it's fine that way.
Okay.
So it's actually more cumbersome to try to be incremental on M. Here, the time is so little that for now we're in a regime where it seems to be fine just doing that.
So it doesn't matter. You leave lambda. You don't want to. Yeah.
We cross-validate lambda.
And the other question.
And for M, we actually go to
the top. Yeah, memory constraint. And you have top 5 classification?
No, this is, as it says here, this is not yesterday result. It's like 5 days ago result.
Thanks.
So in terms of regularization, say it's equivalent like to take M and to regularize, but the accuracy results are different, right? Like, I mean, on some data sets, Falcon is better in terms of accuracy, and on other data sets, not. So some of them are classification, of course, and it's another loss function. But so can we evaluate what kind of regularization it does to take subsampling the kernels? Is it equivalent to lambda norm of F?
Yeah, in a sense, yes.
But why does it not give the same results?
What do you mean it doesn't give the same
in terms
results?
of accuracy? Like if you compare with
ridge regression, say.
Yeah.
Oh no, it's basically, so there are 2 reasons. One is purely computational. Again, it's just that, this stuff dies along the way, and so now try to do a good, so a basic thing is that if you have an algorithm that takes 5 minutes to train and an hour to train, you can try, 10, 20, 100 regularization parameter. If it takes a week to train, how many are you going to try? Okay? So typically, speed of training directly translates in your ability to spend more time tweaking the parameter. And since tweaking the parameter, especially when you use least squares, matters a lot, then this directly translates in performances.
And so if it's classification and not least squares, it will be different from lambda norm of F?
No. I mean, all these algorithms, so it depends. I mean, depends a bit what you mean by that. So all the algorithms that you see here that have KRR, Nystrom, ADMMRF, BCDRF, BCD Nystrom, everything but, I would say, deep neural networks are all based on variation on the theme I discussed these days. SGD. The only different ingredient that I didn't discuss is splitting the data and doing what they call this divide and conquer. All the other ones are basically doing the same, and the difference are really more in again, the amount of time you can spend on tuning things because of the constraint in terms of computations.
Okay.
But and that's why I'm not emphasizing that much, the difference in performance is not that dramatic. I'm not sure that's the main thing. Here, I'm really comparing different priors, if you want, because it's a deep neural network on the one hand, or a boosted decision trees on one hand, and our method. My prejudice in this kind of practical situation is that I'm not sure that this difference is going to be because of, I'm still not sure that this is because of the neural network use a different prior than our method. I'm more lean to think that it's because they use 5 times more parameters. So I want first exclude that option, and then if I really still see a big gap, then I'm going to work a bit more, and then otherwise it just means that really they just have better prior and they get better result. But we have some, 3 hours against 78 on a cluster still to spend to understand that.
Okay, thank you.
That's it.
thank you for your talk. First, really appreciate it. So you present a supervised learning problem where you have all this, but regularization can also be applied to unsupervised learning. So have you tried your method on unsupervised learning models? Because what you've seen, so what would you expect?
I have something here, a big list of things with names. Let's see if I find it. Oh, maybe I don't have it. So it's my daughter. No, we haven't tried. So I know that there are some results. So essentially, this is a plug and play kind of ideas for anything which is kernelized. Kernel k-means, kernel PCA, kernel pairwise, kernel this, kernel that. You know, the idea is just go stick to the least squares and just plug it in. This stuff is 1 month old. Okay. So again, I think we're trying to gain enough momentum to see that you can actually, whenever you're still using those kind of one-layer tools somewhere, this is just going to make your life easier. And I believe, I don't see any reason why you should not give a big boost in a lot of other problems where you do similar computation. Somewhere we use special properties of supervised learning. In a lot of cases, you see it's just a bunch of linear algebra. So I expect it to be applied very broadly whenever you can reduce to just use linear algebra tools.
Thanks. I have another question. Everything that is trained here, even your method is batch learning, right? You use
so far, yeah.
So you compare to the Fourier features, the random Fourier features,
yep.
And well, it performs much better in computational time. But random Fourier features can be used for online learning rather than Nystrom methods, which require some SVD decomposition and stuff like that.
So it's not quite true. So there are a couple of things. So the question is about, okay, why do you work in batch rather than stochastic, okay? So there is, you're essentially right. Let me just notify one small detail is you can also use Nystrom online. What you do is basically that you keep endpoints, you do a Cholesky decomposition of this matrix once and for all, and then you just go online, okay? So you don't need to increase memory all the time. You can still work on a smaller subset. This aside, the thing is that in our experience right now, this method destroys a stochastic gradient method if you can allow yourself to look at the data more than once. Okay, so there is a bit of a, I think when I start agreeing a bit of disconnect between reality and practice, between theory and practice. So there is this thing that take without qualification is if you have a lot of data, use stochastic gradient methods because they require less memory. Well, if you actually have to pass over the data, say 5, 10, or 100 times, at this point you have to wonder whether you should use an accelerated method or a stochastic gradient method. So this has become kind of a mantra because in deep learning it's really the case that they work better. But in convex problem, if you go over the data, if you can allow yourself to go over the data more than once, you typically get better result. And accelerated methods and stochastic methods, they basically, it's true that you have to wait to see all the data before you update your solution, but you're going to do it anyway. So waiting 100 iteration and a half or 101 iteration doesn't really matter. So one question I always ask is, sincerely, if you can provide me example of data sets which are big, where you can allow yourself to look at the data a few more times, and stochastic gradient destroys this method, because we have never found them. Okay? Then again, if you really can look at the data only once, then random features could be used. We know, we haven't done it yet, but we know how to do the preconditioning for random features. And then the question is, can you use random features with preconditioning approximated and stochastic gradient and put everything and show that you get something more? I don't think we can prove it. Because stochastic gradient improvement is just, as I said, is that the beginning is an empirical observation. So in practice, I think it can be done, and I should mention that the work, one of the few work that are competitive to ours is this, Again Pro, is doing something along the line. He's using some kind of random features as GD and some preconditioning. Yeah, so but this is what's going on. So I agree that it's something that needs to be done. I think also the question has to be taken with a bit of qualification to really see, are you really just going to do one pass over the data, or are you doing 5 or 10? Because if you're doing 5 or 10, this is probably going to be just fine.
Thank you.
Yeah.
Is there any questions?
I don't know. It's a lot of stuff. I don't remember. This is. I don't remember what they do there. This is the SVM, right? I don't remember. This is the most recent code for SVM. It's called SVM Liquid. Is a code that was released a few months ago, and it's just not a single machine. I don't remember what it is. It's at least 14 times what we do.
Questions? Okay, so let's warmly thank Lorenzo for his lectures. Just a few words for conclude this summer school. I would like to thank the Institut Henri Poincaré for their helps. In particular, the video recording team, the CRUS, which is independent of Institut Henri Poincaré, but which has provided the food, and also the secretary involved in the process of organizing this summer school. I would like to thank the sponsors, institutional sponsors. So you have a bunch of logos on the website, and also to close this event, we need some feedback on your feeling on the summer school. So if you can take just 5 or 10 minutes to fill the form, it will help us to organize other summer schools like this. So we have sent an email we will send an email with the to have some feedbacks on the summer school. So I'm not forgetting something. There is a YouTube channel also on the. So you will find the link on the website if you want to see all the videos and of the speakers. You will find the link on the website. And so I would like to thank the speakers again. So Anders, Andrea, Francis, Emily, Claire, Carlos, and Lorenzo. Thank you very much for all your work and for making this summer school great. I think so. Thank you very much. And thank you for attending this summer school.